Hello everyone, welcome to my channel. This is Rekha Venkateshwarlu, Assistant Professor of Physics, Government Degree College for Women, Nalgonda. In the present class, now I am going to present the topic Ballistic Galvanometer. This is B.Sc Physics 5th semester Electromagnetic Theory Unit 2 syllabus. The contents of the present lecture are Introduction, Deadbeat Galvanometer, Ballistic Galvanometer, Principle, Construction and Theory. After that, we will discuss the charge sensitivity and current sensitivity of galvanometer. Next, uses of ballistic galvanometer. After that, comparison between ballistic galvanometer and deadbeat galvanometer. Next, electromagnetic damping and critical damping. Lastly, we will see the summary of the lecture. In the last class, we discussed that when the current carrying conductor placed in the uniform magnetic field of induction B, that will experience the force F bar equal I into L bar cross B bar. Its magnitude F is equal ILB sin theta. For example, this is the uniform magnetic field direction. Now, this is the current carrying conductor carrying the current I. It is making angle theta with the field direction. Then the force acting on the conductor is given by F bar equal I into L bar cross B bar. Okay. So if the conductor is parallel to the field direction, then no force acts on it. If the conductor is perpendicular to the field direction, then maximum force acts on the conductor, F maximum equal to ILB. So when the current carrying conductor is perpendicular to the uniform magnetic field, then that experience the maximum force F maximum equal to ILB. And one more point is, when the current carrying coil is placed in the uniform magnetic field, then the torque acts on it, tau equal to BIAN sin theta. In vector form, we write it as tau bar equal M bar cross B bar, where theta equal to 90 degrees, then tau maximum equal to BIN. In that formula, where B stands for magnetic field induction, I amount of current flowing through the coil, A area of the coil, N total number of turns. So now, so what is this? So for example, this is a coil, rectangular shaped coil, which is placed in the uniform magnetic field of induction. So here the pen is pointing the direction of field direction. In this case, the plane of this one, the plane of coil is parallel to the field direction. Then the perpendicular drawn normal to the plane is right angles to the field direction. So when the plane of the coil is parallel to the field, or the normal drawn to the plane of the coil is perpendicular to the field direction. So in this formula, we take theta equal to 90 degrees, then tau maximum equal BIAN. If the plane of the coil is like this, it is perpendicular to the field direction, then normal drawn to this plane also in the same direction. In this case, we take theta equal to 0, tau equal to 0. So simply the conclusion is, when the plane is parallel to the field or the normal to the plane is perpendicular to the field, then maximum torque acts on the coil, tau maximum equal to BIN. So keeping these points in mind, so let us start the discussion of ballistic galvanometer. So before that, what is deadbeat galvanometer? A moving coil galvanometer or an ordinary galvanometer used to measure the steady current is called as deadbeat galvanometer. I think you studied at your intermediate level about this. The second one is ballistic galvanometer. That is the actual topic now. We are going to discuss this one. This is a galvanometer used to measure the total charge that passes through it in a given time, not as a steady current, but as a sudden discharge is called as ballistic galvanometer. Okay. Now, the principle of ballistic galvanometer is, it is specially designed galvanometer suitable for measuring charge which is displaced by a varying current of short duration, such as in the charging and discharging of a capacitor. When such a varying transient current is passing through the galvanometer, then the coil will begin to perform angular oscillations about its axis. In this, the maximum deflection is proportional to the total charge passing through the galvanometer. So this is the figure of ballistic galvanometer, right? Now, if you observe this figure, right? So this is a rectangle shaped coil having a large number of turns, right? So that is made with a insulating copper wire wound on non-metallic frame like ivory or boom or ebonite. The upper end of the coil is connected to the screw T1. The bottom end is connected to the screw T2 by means of phosphor branch spring. Here the coil is suspended by means of phosphor branch wire between two strong magnetic horseshoe magnetic poles. Here these are the cylindrical shaped magnetic poles. Then they generate the radial magnetic field. So the importance of radial magnetic field is, due to this radial magnetic field, always the plane of the coil is parallel to the magnetic field. Then the maximum torque acts on the coil. Here M is the plane mirror which is placed on this phosphor branch wire. Here the deflection of this coil is measured by using the lamp scale arrangement. Okay. So what I am saying is, so in this, the construction, it consists of a rectangular coil ABCD, which is having the more number of turns with a thin insulated copper wire wound over a lightweight non-conducting rectangular frame of ivory or bamboo. The upper end is connected to the phosphor branch wire. That coil is suspended between the poles of strong horseshoe magnetic poles N and S. The ends of the magnet are cylindrically curved so that radial magnetic field is forming between the poles. The bottom end of the coil is connected to the rigid screw T2 by using the phosphor branch spring. The upper end is connected to the screw T1, right? Now, a small circular plane mirror M is attached to the suspension wire. So by using the lamp scale arrangement, we measure the deflection that is situated at 1 meter distance from this arrangement. The light falling on the plane mirror getting deflected and a bright cross wire image is formed on the scale. This total setup is placed in the backlight box, and the reflected light from the suspended mirror will come out through the glass window which is arranged opposite to the mirror. The ballistic galvanometer is made to be in horizontal plane by using the leveling screws which are provided at the bottom of the instrument. This is about the construction of ballistic galvanometer. Now what is the working? When the current is passing through this coil for a short time dt, then the charge Q equal I dt will flow through the wire. So due to the couple acting for a short duration, then angular impulse tau into dt will act on the coil. As a result, the coil makes oscillations. Okay. Now, so here this is the working of this coil, the working of this moving coil galvanometer. We can understand from this figure, right? Imagine this is a rectangle shaped coil A, B, C, D, right? The current is flowing in this direction. So there in the figure, the arrow mark represents the current direction. Okay. Now, here AB and CD are the breadth, AD and BC are the lengths. Okay. Now, AB and CD sides are parallel to the field direction. In the figure, B bar represents magnetic field direction. So the sides AB and CD are parallel to the field direction. So therefore, no force acts on these two sides. But the sides AD and BC are perpendicular to the field direction. Then maximum force acts on it. Since the coil has n number of turns, then according to F maximum equal ILB formula. On the sides A, D and BC, BINL maximum force act. Applying the Fleming left hand rule, on the side AD, the force BINL acts perpendicular to the plane of the paper inward direction. On the side BC, BINL force acts that is as shown in the figure. Okay, so simply if you imagine this book as a rectangular coil, here the current direction is like this. The current direction is like this. What is the Fleming left hand rule? If the three fingers, the left hand three fingers are stretched perpendicular to each other, the middle finger, the forefinger representing the field direction, the middle finger represents the current direction, then thumb denotes the force acting on the conductor, right? So on the side AD, the current direction is in this direction, B bar field direction. Now the force direction is like this, that is perpendicular to the plane inward direction. So coming to the side BC, here current direction is in the middle finger direction. B bar direction is denoted by the forefinger. Then the thumb denotes the force direction. So therefore on this side, force acting perpendicular to this length inward direction, here upward direction. So on the coil at two different positions, two equal parallel forces are acting in the opposite direction. Therefore, they constitute the couple. Okay. So this is the concept of torque acting on the coil. Now the force acting on the coil having n number of turns due to the magnetic field B is F is equal BINL. So that is we discussed just now. Since two equal and parallel opposite forces acting on the sides AD and BC, which are constituting the couple, and thereby torque acts on the coil. Therefore, the torque is given by torque is equal force into perpendicular distance. So any one of the force BINL into perpendicular distance here, that is breadth, equal to BIAL. Okay, where L into B, length into breadth, equal to area of the coil, that is substituted here. Okay, now, but the torque acting for an infinitesimal time dt gives the angular impulse to the coil. Therefore, angular impulse is equal the couple into time. So what is the formula? Angular impulse is equal to torque tau into time in duration dt. So couple is the BIAN into dt written. Then total angular impulse in the time interval t is given by integral 0 to t BIAN dt. That is called BAN are constant written outside of the integral 0 to t I dt. But integral I dt gives the charge flowing through the coil, that is Q. So then total angular impulse acting on the coil in the time interval t seconds is BAN Q. Okay. Since angular impulse gives the coil angular momentum I omega, where I is moment of inertia, omega angular velocity just impulse has passed. So therefore, we are equating these two, BANQ equal to I omega. This is say equation 3. The torque acting on the coil utilized as rotational kinetic energy in twisting the suspension wire. So therefore, initially rotational kinetic energy of the moving system, since it has the angular velocity omega, its rotational kinetic energy equal half I omega square. This rotational kinetic energy is utilized to twist the suspension wire, then that will comes to the rest. Therefore, final kinetic energy equals to 0. Then the decrease in kinetic energy equal half I omega square minus 0, that equal half I omega square. But here we consider that the damping is absent. We are taking that condition. Then the decrease in rotational kinetic energy is used for doing work in twisting the suspension wire. If C be the restoring couple per unit twist and theta be the deflection of the coil, then couple for the twist theta is C theta. For unit twist restoring couple, we are taking C. Then for the deflection theta, then restoring couple is given by C theta. Okay. The work done for additional small twist d theta is given by d double equal c theta d theta. C theta d theta. This is analogous to the work done equal to force into displacement. In the case of rotational motion, we write d double equal to tau into d theta. So here that is the c theta d theta. So using that formula, we are writing d double equal c theta d theta. If the maximum angle of twist is theta naught, then the total work done is given by double equal to integrating of this dw equal integral theta equal to 0 to theta naught c theta d theta, right? But c is constant, theta d theta integration c theta square by 2. Applying the limits, we get half c theta naught square, equation 5. Therefore, half I omega square equal to half c theta naught square. So then we can write I omega square equal c theta naught square, say equation 6. From equations 3 and 6, dividing the equation 3 with equation 6, we get I square omega square by I omega square equal right side b square a square n square q square by c theta naught square. So left side I cancel, omega square cancel, only I is left. So therefore I is equal b square a square n square q square by c theta naught square, say equation 7. But the time period of oscillation of the coil is given by t equal to pi root of I by c, right? So here squaring both sides, t square equal 4 pi square I by c. From that you write I as the subject, I equal ct square by 4 pi square. Okay, equation 8 and 9. From equation 7 and 8, we can write ct square by 4 pi square is equal to, so there I value substituted, b square a square n square q square by c theta naught square. So therefore q square is equal c square t square by 4 pi square b square a square n square into theta naught square. But we require the expression for q, therefore writing q as the subject, q equal to square root of this right side t by 2 pi c by b a n into theta naught coulombs. So this is the expression for charge which is flowing through the coil of the ballistic galvanometer. Say this is equation 10. In this expression, K equal to C by BAN, which is called as current reduction factor of the ballistic galvanometer, right? If you observe this formula, all these factors are constants keeping, then Q depends on theta naught. So Q directly proportional to theta naught, say equation 11. So what is that? The charge flowing through the galvanometer is directly proportional to maximum angle of twist theta naught, where theta naught is maximum angle of twist of the coil. Okay. Now, here we talk about sensitivity of the galvanometer. That is two types. One is charge sensitivity. The second one current sensitivity. So, charge sensitivity is nothing but what? This is amount of charge required for unit deflection is called as charge sensitivity. So we have the formula for Q what? Q equal to T by 2 pi C by B A N theta naught. In this, if you substitute theta naught equal to 1, that is the unit deflection, then you will get Q equal to T by 2 pi C by B A N. That is charge sensitivity. Therefore, we are writing charge sensitivity equal T by 2 pi into C by Bn. How we are defining? This is amount of charge required to produce the unit deflection is called charge sensitivity. The second one is current sensitivity of the galvanometer. Similar definition. The amount of current required for unit deflection in the galvanometer is called as current sensitivity of the galvanometer. Here charge sensitivity and current sensitivity are related as charge sensitivity equal T by 2 pi times to the current sensitivity. In this expression, if you substitute T equal 2 pi second, then charge sensitivity equal to current sensitivity. So, for the time period of the coil of the ballistic galvanometer 2 pi seconds, then charge sensitivity equal current sensitivity. Okay. So what are the uses of ballistic galvanometer? By using the ballistic galvanometer, we can compare the electromotive force of two cells, to compare the capacities of two condensers, to measure the self-inductance of a given coil, to measure the mutual inductance of a coil, to measure high resistance by leakage method, to measure thermo EMF, and to measure the strong magnetic field using a search coil, and also to determine magnetic susceptibility and magnetic permeability of magnetic substances, and to measure the angle of dip at a place, we use this ballistic galvanometer. These are the uses. What is the damping of ballistic galvanometer? So the coil oscillates with a decreasing amplitude due to the two reasons. One is due to the frictional force between moving system and the surrounding. The second one due to the electromagnetic damping. So therefore, the coil oscillating with a decreasing amplitude due to the frictional forces between moving system and surrounding medium, that may be viscosity of air, and also in overcoming the electromagnetic damping. This is called damping of the ballistic galvanometer. So here we talk about the two types of damping. One is electromagnetic damping, the second one critical damping. So what is the electromagnetic damping? The damping which arises due to the induced current in the coil during its motion in the permanent magnetic field is called electromagnetic damping. So what does that mean? So here, since the coil is rotating in the magnetic field between the magnetic poles of horseshoe magnetic poles, there the conductor, the current carrying coil is in the motion in the magnetic field. Then EMF will be induced. According to Lenz's law, the EMF induced in that coil will oppose the motion of that coil. That type of damping is called as electromagnetic damping. So therefore, it is due to the induced current in the coil during its motion in the permanent magnetic field. Okay. The second one is critical damping. So here the moving coil galvanometer, that is ballistic galvanometer, is connected in the external circuit to having some resistance. The particular resistance for which the motion of the coil of galvanometer just ceases to be oscillatory is called as critical external damping resistance, and the galvanometer is said to be critically damping. So here three conditions are there. For more resistance of the circuit, over damping. If the resistance of the circuit is less, under damping. For certain sufficient smaller resistance, then the galvanometer ceases to be oscillatory. That condition is called critical damping. Okay, so this is critical damping. Now, coming to the next concept, what are the differences between ballistic galvanometer and a deadbeat galvanometer? So, based on our discussion as of now, so we can compare these two. In the ballistic galvanometer, the coil is wound on a non-metallic frame like ivory or bamboo to reduce electromagnetic damping. But here, the coil is wound on the metal frame to increase the electromagnetic damping. In ballistic galvanometer, the coil is oscillatory due to the damping. Here it is non-oscillatory due to the larger damping. In the ballistic galvanometer, the momentary passage of charge causes impulse on the coil. Therefore, the torque is zero when the coil rotates. Here the coil rotates due to the constant torque. This is the main difference. It measures the charge. It measures the steady current. The charge is measured by throw of galvanometer in this. Here the current is measured by steady deflection in galvanometer. So these are the differences between ballistic galvanometer and ordinary moving coil galvanometer or deadbeat galvanometer. The summary of this lecture. So what we discussed now, the torque acting on the current coil when it is placed in the uniform magnetic field is given by tau equal B.I.A.N sin theta, where theta is angle between normal drawn to the plane of the coil and the external field direction. The ballistic galvanometer measures the total charge that passes through it in a given time, not as a steady current, but as a sudden discharge. You remember this part. And one more point to be remembered is, in ballistic galvanometer, the charge flowing in it is directly proportional to maximum angle of twist theta naught. Here the expression for Q, T by 2 pi into C by BAN theta naught coulombs. So the reduction factor of ballistic galvanometer K equals C by Bn. The charge sensitivity of this ballistic galvanometer formula T by 2 pi into C by Bn. Relation between charge sensitivity and current sensitivity is T by 2 pi into current sensitivity. Okay. Uses of ballistic galvanometer to compare EMFs of two cells, to compare the capacitance of the given two condensers, to measure the self-inductance of a coil, to measure the mutual inductance of a coil, and to measure high resistance by leakage method, etc. So after that, we covered the discussion of electromagnetic damping and critical damping, right? So electromagnetic damping is nothing but it arises due to the induced current in the coil as it is in the motion in the permanent magnetic field. The second one, critical damping, is nothing but, so for a particular resistance of the circuit in which the galvanometer is connected, then the galvanometer just ceases to be oscillatory, is called critical external damping, right? So this is about this lecture. Thank you.